Welcome students. So, let us continue with the design of 3-phase induction motor module. So, we are discussing about the choice of ampere conductors per meter in the design of induction motor. So, first one we have to consider for this one in the choice of ampere conductors per meter is copper loss and temperature rise. A large value of AC means here ampere conductors means that the greater amount of copper is employed in the machine. So, if the value of AC is increases, so then there may be an increase in the copper which is placed inside the induction motor. So, which results in higher copper loss because the number of copper windings or the number of turns in the copper are increases. So, which results in higher copper loss and large temperature rise of the embedded conductors. So, the conductors which are placed inside the induction motor or in the stator or rotor. So, there will be large temperature rise takes place if you increase the number of large value of AC ampere conductors in the induction motor. So, next, what is the effect of voltage? A small value of AC should be taken for high voltage machines, as in their case the space required for insulation is large. A small value of AC, if you consider, should be taken for high voltage machine. So, the high voltage machine, so the area required for the insulation is large, correct. So, if you increase the number of AC or the value of AC, then there will be no space for the insulation. So, for high voltage machine, the value of AC should be taken as small, as it is required for the insulation, correct, space required for the insulation. Next, overload capacity, a large value of ampere conductors which will result in large number of turns per phase. Large number of turns per phase will be increases. This would mean that the leakage reactance of the machine becomes high. Leakage reactance of the machine will be increases, and the parameters or performance of the induction motor will be drawn through the circle diagram, correct. So, the overload capacity of the induction motor is calculated by the diameter of the circle diagram, correct. So, if you increase the overload capacity, the large value of ampere conductors would result in large number of turns per phase. The diameter of circle diagram will be reduced, results in reduced value of overload capacity. So, if the diameter of circle diagram is large, then the overload capacity of the induction motor is large, and if the diameter of circle diagram is reduced, which will reduce the overload capacity, which in turn reduces the ampere conductors. Hence, the value of ampere conductors per meter depends upon the size of the motor, value of stator winding. So, ampere conductors per meter depends upon the how much size of the motor and the value of stator winding. So, value of AC varies between 5000 to 45,000 ampere conductors per meter. So, normally the value of ampere conductors is chosen as 5000 to 45,000 ampere conductors per meter. Now, what are the main dimensions of induction motor? The main dimensions of induction motors are the diameter of stator board, that is capital D, and the length of the stator core, that is L. So, in the previous figure we have seen that. So, stator board diameter is capital D and the length of the stator core is capital L. So, that is the main dimensions of the 3-phase induction motor. The product D square L is determined from input kVA, specific electrical and magnetic loading. Specific electrical and magnetic loading, the product D square L is calculated. The product D square L is determined from the input kVA of the induction motor, specific magnetic loading and electrical loading. The separation D and L from D square L depends upon the ratio L by tau value. L by tau, where tau is the pi D by P. It is called as a pole pitch. Tau is called as a pole pitch, that is the number of conductors per pole. The number of conductors placed per pole is called as a pole pitch. So, the separation of D and L, diameter, stator bore diameter and the length of the stator core depends upon the ratio of L by tau. L by tau, where tau is the pi D by P, which is called as a pole pitch here. Okay. That means in the numerical problems they will give the ratio of L by 2 value for a particular induction motor. So, based on that one you have to calculate the value of D and L. In induction motor, most of the operating characteristics are decided by L by 2 ratio of the motor. So, the induction motor L by 2 ratio will be the deciding operating characteristics, deciding factor of the operating characteristics of the induction motor. Ratio of core length to pole pitch is decided based on the following values. For minimum cost, we have to consider L by 2 value as 1.5 to 2. L by 2 value is 1.5 to 2 if it is there, then we can consider it as a minimum cost. For good power factor, the value is 1 to 1.25. L by 2 ratio is 1 to 1.25 for good power factor, or we can choose this one also, that is square root of 1.8 into L, or 2 is equal to 0.18 into L to the power 0.5, that is square root of 0.18 into L for the good power factor, or you can choose 1 to 1.25 value, the ratio of L by 2. So, either depends upon the question it is, if it is you are designing for minimum cost or good power factor, you have to choose the L by 2 value. Now, next we have to consider the stator winding. For small motors up to 5 HP, single layer winding is considered. If your induction motor is up to 5 HP, so the single layer winding is considered. Single layer winding means only one conductor per slot, one conductor per slot. So, that is a single layer winding, stator winding. We are considering only the stator winding. For large capacity machines, double layer windings are employed with the diamond shaped coils. The coils are diamond shaped and double layer windings are employed for large capacity machines. Double layer means two conductors in a slot. Two conductors are placed inside the slot with the diamond shaped coils. The stator winding can be designed for either star or delta depending upon the running condition. Stator winding can be considered as either star or delta for the depending upon the running condition. Now, stator turns per phase. How to calculate the stator turns per phase? The turns per phase TS, S stands for stator. The turns per phase TS can be estimated from stator phase voltage and maximum flux in the core. So, it is calculated from the stator phase voltage and maximum flux in the core. The maximum flux in the core can be estimated from BAV, that is average flux density, and D, stator bore diameter, L, that is stator core length, and number of poles. Specific magnetic loading BAV is calculated as P5 by pi dl. So, in the initial class we have studied that specific magnetic loading BAV or average flux density we can say, which is calculated by P5 divided by pi d into L. So, here phi is nothing but phi m, that is maximum flux. So, you can substitute phi m equal to BAV into pi dl divided by P. So, rearranging this equation, phi m is maximum flux, phi m equal to BAV into pi dl by P. Stator phase voltage ES is calculated as 4.44 kWs into F into phi m into TS, where kWs is stator winding factor, S stands for stator, kWs is stator winding factor, and F is the supply frequency and phi m is the maximum flux into stator turns, that is the stator phase voltage. Stator turns per phase TS, from this one you can calculate it as ES divided by 4.44 kWs into F into phi m, where kWs is stator winding factor, which is equal to normally 0.955. So, if it is not given in the numerical problems about the kWs, that is stator winding factor, we can assume it as 0.955. Okay. Now, stator conductors. So, this is the equation you can calculate the stator turns per phase for a induction motor. Now, stator conductors. How to choose the stator conductors? Current density in the stator winding is usually taken as 3 to 5 amps per millimeter square. So, current density is current per unit area, correct. So, current per unit area in terms of millimeter square, area is considered in terms of millimeter square. So, current density in the stator winding is usually taken as 3 to 5 amps per millimeter square. So stator current per phase IS is calculated as Q, that is a kVA rating of induction motor into 1000. So you are converting into VA divided by 3 into ES. So we are considering the per phase voltage 3 into ES. So 3 into phase voltage into phase current, you will be getting the Q. Q is the in terms of kVA, and if you multiply by 1000, you will be getting in terms of VA. So therefore stator current per phase IS is calculated as Q into 1000 divided by 3 into ES. Area of each stator conductor AS is given by IS into delta S. So area of each stator conductor. So delta S is nothing but stator current density. Delta S is nothing but IS by AS, correct? IS by AS. So area of each stator conductor is AS is equal to IS into delta S. So where delta S is the current density in the stator conductor. For lower value of current, round conductors would be best convenient to use. For if the current value is lower, that is stator current is lower value, so you can choose the round conductors, that will be convenient to use. For higher value of current, bar or strip conductors would be more convenient. So the current value is higher, more than 200 or 300 amps. So the strip or bar conductors can be used. So that is more convenient when compared to round conductors for the lower value of current. Next, design of stator core. How to choose the stator core? The stator core is made up of laminations of thickness 0.5 mm. So stator core is having the laminations which having the thickness is 0.5 millimeter. So the design of stator core involves selection of number of slots, estimation of dimensions of stator teeth, and depth of the stator core. So design of stator core is having 3 steps. One is selection of number of slots, what is the number of slots you have to choose, and estimation of dimensions of the teeth, stator teeth, what is the dimension of stator teeth, and what is the depth of the stator core. So based on this one, we can design the stator cores. Now stator slots. What is meant by stator slots? What is the dimensions of stator slots? That you have to see. The different types of slots used in induction motor are open slots and semi-enclosed slots. So there are, you can say, 3 types of slots which can be used in the stator. One is fully enclosed slots, and semi-enclosed slots, and open slots. So 3 different types of slots can be used in the induction motor: open slots, semi-enclosed slots, and fully enclosed slots. The shape of the slots have effect on performance of the motor and problem of installing the winding. So why you have to choose open slots or semi-enclosed slots or fully enclosed slots? So choosing of these type of slots will be having the effect on the performance of the induction motor, and during the construction of induction motor it will have the effect on installing the winding which are inside the installing the copper winding or the conductors inside the slots. So it will give the problems. So this is the example, stator geometric location of the coil winding. So this is A is the semi-enclosed. So this is the number of conductors, these 2 are the conductors, and this together is the slots. Together is slots. So this is the semi-enclosed slot, because little bit opening is there, so that is semi-enclosed. So this is a double layer winding, 2 conductors are placed inside the slots. So here also it is a semi-enclosed because small opening is there. So this is the semi-open, you can say semi-open, same thing, BOS, and this is open number of slots because it is fully open. So there are 2 conductors are placed, square type conductors are placed, here round conductors are placed. So here 2 conductors are placed, here 4 conductors are placed, that is 4 layer. Here 2 conductors are placed, double layer, square type or rectangular type, you can say rectangular type of conductors are placed, and it is a fully open, this is fully open type of slots. When open slots are used, the winding coils can be formed and fully insulated before installing, and also it is easier to replace the individual coils. So if the slots are open number of slots, the winding coils can be easily formed. You can easily form, and you can fully insulate it before installing it. So you can easily insulate that one before insulating before installing in the slots. And also it is easier to replace the individual coils. Individual coils you can replace if it is any problem, if it is a open slots. Open slots avoids excessive slot leakage, thereby reducing the leakage reactance. So slot leakage will be excessive slot leakage will be avoided, and therefore there is a reducing in the leakage reactance takes place. When semi-enclosed slots are used, the coils must be taped. So you have to provide a taping of the coils. So that means covering the coils with the tape, a thread, or you can say a cloth. So when the semi-enclosed slots are used, the coils must be taped. It is fully covered with the cloth and insulated after they are placed inside the slot. So insulation can be done after placing inside the slot. So it is not insulated before placing in the slot. In the open slots, you can insulate before placing in the slot. In the semi-enclosed, it is insulated after they are placed inside the slot. The advantages of semi-enclosed slots are less air gap contraction factor, giving small value of magnetizing current. So what is the advantage of semi-enclosed slots? So the air gap will be less, or you can say air gap contraction factor when the induction motor is rotating continuously. So if the semi-enclosed slots are there, then there will be less air gap contraction factor. So air gap contraction will be less, which will give the small value of magnetizing current. IM value will be slow or less, you can say, and low tooth pulsation loss. So when the induction motor is running in continuously with high speed, so there will be a pulsation loss takes place. Tooth pulsation loss. What is meant by tooth? So the edges of slots, you can say edge of slots, whether it is a semi-enclosed or fully enclosed. So you can say that is the tooth of the induction motor. So when it is highly continuously rotating with high speed, so if it is a semi-enclosed slots, so there will be a low tooth pulsation loss can be achieved, and less noise also less when compared to the fully enclosed or open type slots. So if you consider open type slots, the noise level is less in case of semi-enclosed type slots, and tooth pulsation loss also less. Semi-enclosed slots are mostly preferred for induction motor. So because of this one, because of low value of magnetizing current, low tooth pulsation loss, and less noise, so normally semi-enclosed slots are preferred in the induction motor when compared to open slots, fully open slots. Next, we have to consider the choice of stator slot. How to choose the stator slots? The number of stator slots depending upon the tooth pulsation loss, leakage reactance, ventilation, and magnetizing current, and iron loss and cost. So the choice of stator slots depends upon the following factor: tooth pulsation loss. When the induction motor is continuously rotating, there will be a tooth pulsation loss takes place. So the number of stator slots depends upon that tooth pulsation loss. Leakage reactance, what is the value of leakage reactance? Ventilation, what is the provision of ventilation? Magnetizing current, IM value, what is the value of magnetizing current? Iron loss, and the cost. Based on these factors, or by considering these factors, you have to choose the number of stator slots. Number of slots should be selected to give an integral number of slots per pole per phase. So if you consider the slots per pole per phase, number of slots per pole per phase should be an integer. It is not a fraction number. If there are 36 number of slots and 4 pole machine and 3 phase machine, so 36 divided by 4 into 3. So 4 into 3 is 12. So 36 divided by 12. So 3 is the number of slots per pole per phase. So that should be integer. You cannot choose the number of slots which will give the fraction slots per pole per phase. We should give the fully integer. Okay. The slot pitch at the air gap for open type of slot should be between 15 to 25 mm. So slot pitch for at the air gap, if it is open type slots, so that should be considered 15 to 25 mm. For semi enclosed slots, the slot pitch may be less than 15 mm. For semi-enclosed slots, you have to choose the slot pitch will be less than 15 mm. So you can calculate the stator slot pitch by this equation YSS. YSS is the stator slot pitch, which is equal to gap surface divided by total number of stator slots. Gap surface divided by total number of stator slots. So SS is the total stator slots and pi d is the gap surface. Pi into d. D is the stator bore diameter. So that is the gap surface. So SS is the stator slots. Total number of stator slots. So you can calculate YSSC is nothing but pi d divided by SS. So SS is nothing but pi d divided by YSS. So stator slot pitch will be given for a particular machine. It is decided by the designer. It is 15 to 25 mm. So based on that one 15 to 25 mm. So you have to choose the number of stator slots by this equation. That is SS is equal to pi d divided by Y into SS. So total number of stator conductors equal to, what is the total number of stator conductor after choosing the stator slots? So stator slots you can choose by this equation, and total number of stator conductors equal to number of phases into conductors per phase. So number of phases, if it is 3 phase, normally if it is a double layer, so two conductors per phase, so it will be equal to 6 into Ts. So Ts is the stator number of turns, stator turns. So 2 into Ts, so it is 6 into Ts. So that is the total number of stator conductors, where Ts is the turns per phase. So conductors per slot, how to calculate the conductors per slot? So ZSS, conductors per slot notation is ZSS. So it is total stator conductors divided by number of stator slots. So total stator conductors is 6 into Ts divided by number of stator slots is S into S. So now what is the guideline for selecting the stator slots? What you have to consider when you are choosing the number of stator slots? So stator slot pitch varies from 15 mm to 25 mm. So you have to, it is given. So you have to consider only 15 to 25 mm is the stator slot pitch for a particular induction motor when you are designing. 15 to 25 mm is the stator slot pitch. Calculate the range of stator slots using this equation, that is stator slots SS is equal to pi d divided by Y into SS. Minimum number of stator slots are obtained when YS is equal to 25 mm. So you have to choose YS as 25 mm because it is in the denominator. So you will be getting minimum value of stator slot SS, since it is a denominator, correct. So when you are choosing 25 mm which is in the denominator, so minimum number of stator slots is you will be getting. Maximum number of slots are obtained when YSS is equal to 15 mm. So 15 mm is the less value. So you will be getting maximum number of stator slots when you are choosing 15 mm. So that is the stator slots. Second method is, or second step is, it is not method, second step is stator slots should be multiple of Q. Q is slots per pole per phase. So stator slot should be a multiple of Q. So Q value should be a fully integer, it is not a fraction value. So Q is the slots per pole per phase. For Q is equal to 2, 3, 4, etc. Calculate the stator slots. So when you are choosing, you have to go by choosing the stator slots per pole as 2. What is the number of stator slots? When you are when is stator slots per pole for phase, that is Q is 3. What is the number of stator slots? When it is 4, what is the stator? What is the total number of stator slots? So that is you have to calculate. Calculate the stator slots. That is SS is the number of phases into poles into Q. So that is the number of stator slots. Now what is the third step? Select the choices of stator slots which are common between the values obtained in step 1 and 2. So based on the step number 1 and 2, what is the number of stator slots? And again you have to refer the statement of the problem. Based on the given statement of the problem and based on the steps number 1 and 2, you have to choose the number of stator slots. So fourth step is the best choice of stator slot is given by the value of slot in the list obtained in the step number 3 and satisfying the slot loading. So normally in the question, what is the maximum loading of the slots? Maximum loading of the slots is, that is electrical loading. Maximum electrical loading in the slots will be given in the numerical, I mean statement of the problem. So you have to satisfy that slot loading also. So that slot loading is, you can calculate by Iz into ZSS, where Iz is the conductor current in the conductor into ZSS. ZSS is the conductors, total number of conductors. So Iz is current through the conductor and ZSS is the conductor per slot. So if you multiply this one, that will give the slot loading. So normally it will be given in the statement of the problem. So that is a 4-step. Based on that one, you have to choose the number of stator slots. So that is a guidelines for selecting the number of stator slots. Next, area of the stator slot. How to calculate the area of the stator slots? Approximate area of each slot is copper area per slot divided by space factor. Copper area of per slot divided by space factor, you will give the approximate area of each slot. So ZSS is the conductors per slot into area of the slot, AS. AS is area of the slot into ZSS, that is conductors per slot, divided by space factor. You will give the area of each slot. The space factor is normally 0.25 to 0.4. The value of space factor is normally chosen as between 0.25 to 0.4. After obtaining the area of the slot, the dimensions of slot should be adjusted. So when you are getting the area of the slot, so you have to adjust the dimensions of the slot. The slot should not be too wide to give the thin tooth. So you have to adjust the dimensions of the slot so that it should not give the thin tooth, because area of the slot area should not be too wide so that it will give the thin tooth. So you have to adjust based on the value obtained. The width of the slot should be so adjusted such that the mean flux density in the tooth lies between 1.3 to 1.7 Weber per meter square. So you have to consider the flux density. Mean flux density should be within this range, 1.3 to 1.7. So based on this one only, you have to choose the width of the slot. You have to adjust the width of the slot. The width of the tooth should not be too large, as it results in narrow and deep slots. So width of the tooth should not be too large, because the area requirement is area is less, so that you have to be adjust the width of the tooth, because it will have a narrow slots and deeper slots, so that you have to adjust the area, correct. So the width of the tooth should not be too large. So width of the tooth should not be too large. If it is too large, then you have to compromise with the narrow tooth and narrow slot and deep slots. The deeper slots give a large value of leakage reactance. Ratio of slot depth to slot width should be between 3 to 6. So if you provide the deeper slots, that will give the large value of leakage reactance. So you have to be considered. You have to be very careful for choosing the dimensions of the slot. It should not be deeper. So it will give the leakage reactance, large value of leakage reactance. Ratio of slot depth to the slot width should be between 3 to 6. Next, stator teeth. You have to consider the stator teeth. The dimensions of the slot determine the value of flux density in the teeth. The dimensions of the slot is based on the value of flux density in the teeth. High value of flux density in the teeth leads to the higher iron loss and great magnetizing MMF. So what is meant by teeth? That is the edge of the stator slots, whether it is a semi-enclosed or fully enclosed, correct. So that is edge you will be considered as a stator teeth. So the place where you can insert the conductors is semi-enclosed or fully open. So the distance between the two slots, you can say, distance between the two slots, you can consider it as a teeth of the slots. So high value of flux density in the teeth leads to higher iron loss and greater magnetizing MMF. Maximum value of BTS. BTS is the mean flux density in the stator tooth. So maximum value of flux density or mean flux density in the stator tooth, that is the maximum value of BTS, should not exceed 1.7 Weber per meter square. So minimum teeth area per pole is calculated by phi m by 1.7. Phi m is the maximum flux divided by 1.7. So you can calculate the minimum teeth area per pole is phi m by 1.7. So teeth area per pole is nothing but number of slots per pole into net iron length into width of the tooth. So SS by PP, SS is the number of stator slots, P is the number of pole, that is the number of slots per pole, into net iron length, that is Li, into width of the tooth, that is WTS. So that is the teeth area per pole we can calculate. When teeth area per pole is minimum, the width of the tooth will be minimum. So 5m by 1.7, if you equate 5m by 1.7, 5m by 1.7 is also minimum teeth area per pole. So that you can equate. So you will be getting 5m by 1.7 equal to SS by P into Li into WTS minimum, that is width of the teeth minimum. So from this width of the teeth, minimum width of the stator teeth is calculated as WTS minimum, which is equal to 5m by 1.7 into SS by P into Li. 5m is the maximum flux into SS is the number of stator slots divided by number of poles and net iron length. So this is the equation to calculate the minimum width of the stator tooth, that is WTS minimum. So we will stop here. So we will continue in the next class.